up.
Hey Ryan.
Blame me.
Ryan's fault.
Hey Ryan. You need to work on your
Okay.
penmanship.
I do. I noticed you subtracted epsilon.
Yeah.
The,
heard you like
the
that.
symmetry that we want to deal
I thought it
with
was hilarious.
next, not that we want to, the symmetry that we have to deal with next is spherical symmetry. And I have put up here the variables that I'm going to use. You want this to be theta, is that right?
It will
It's not.
work.
It's phi. I used phi last time,
work.
I use phi again. I'm not going to change that. This angle from the, what do you call this, the zenith?
Zenith. It's
Is theta in this terminology here.
that's okay.
It's different in everybody.
And what? And the distance from the origin is little r. At least we're using little r now. Okay. So we assume we have this, do I need to write it down? No, I'll skip a step and write the Laplacian after I've assumed a product solution. So I'm going to assume that V, not volume, R theta phi is R of R.
Careful.
I will go with, you won't like this.
Theta.
P of theta. And so I'm not going to please Brian. S and S. S.
Gamma.
Rho. Phi. Come on. Okay. So that's not the potential now.
So what will be the potential now?
V.
V. Okay? And I'm going to attempt to keep this straight.
Good luck.
All right.
Prepare to feel my
No, I can't do it. Yes.
Quitter.
QPR.
You use what and what?
F.
F of,
RPM.
yeah, that's good too, but I actually, my notes have Q. I'm going to do it Q. All right. So what does our Laplacian look like then? It looks like P, Q, 1 over R squared, d by dr, R squared, R. You've seen this several times in quantum, plus R cubed over R squared sine theta, d by d theta, sine theta, d theta, plus RP R squared sine squared theta d squared q d phi squared equals 0. Okay. Divide through by RP cubed. Multiply through by R squared sine squared theta. Yes, R squared sine squared theta. Yay. I've got something that's here that's only a function of q. On the other side of this relation, is a function of r and theta. All right? So I can suppose that these two things have got to be equal to a constant, right? Once again, because the azimuthal function for the potential has got to come back to itself. Potential is only allowed to be single valued. It means that I'm going to assume a constant here, which is going to give me, and I'm going to choose the constant so that I get sines and cosines, or exponentials, e to the I, complex exponentials. And I'm going to choose the constant to be an integer squared because I want the function to be single valued. Okay? So that means that, maybe I'll put that over here. The solution in Q looks like this. How do I want to write that? I'll write it like this. A sub n sine n pi by, whoops, n pi plus e sub n cosine n phi. And what I did here was to make that whole mess equal to m squared. Okay? Doesn't matter if it's okay. That's what we're doing. All right, so now I've got this thing here that I'd like to somehow isolate the function in theta and isolate the functions in R. And that is not so bad if I divide it all by sine squared theta again now. Well, I multiplied by sine squared theta. Now I get rid of it. Put this back, sine theta, and then I have sine squared theta over here. Put it all on one side of the equation, equals 0. And now I've got just a function of R and just a function of theta. Okay? And this is going to be true, or rather, just a function of R and just a function of theta will be true if each of these expressions is equal to a constant. Now comes the total cheat, because we know what the answer is going to look like. Right? So Mr. Legendre told us all about this. We're going to guess, remember that's an integer, right? We're going to guess that the only way that that could be true is if each side is equal to a constant. That constant is equal to L times L plus 1. Not L squared, but L times L plus 1. Because we know the form that the solution is going to take in the end. Right? So I have my two equations now. I have d by dr, r squared, dr, dr, minus plus, yes, that's right, L times L plus 1 times R equals 0. That's my radial equation. Right? And my angular equation we'll come back to later. That's the complicated one. All right. So this equation here has relatively simple solutions. Again, they're just powers in R. Right? It has the form R of R, the general solution, is going to become A sub L, oops, B, C, C sub L R to the L plus D sub L over R to the L plus 1. And if, in the end, I'm going to be summing over all L's, right? But wait, there's more. So we'll come back to the details of this later, right? We can get an idea of when these solutions are going to apply just by inspection. We can say that if we're solving for the potential in some space outside of a finite volume, so I might have know the potential in here and I want to know what's going on at distance. It's going to, if I had positive powers in there, it would become infinite. And we know that that's not going to be allowed because we're going to, for finite charge distributions, we're going to set the potential at infinity equal to 0. Okay. So that would mean that I'm only going to have solutions, these solutions, for the solution outside of a finite charge distribution. And I'll only have these solutions for a region inside of a finite charge distribution because this would blow up otherwise. So it's a question of finding physical solutions. Right? Mathematically they're allowed, but physically, because of the form the potential has to have. Adam, yeah.
What is the bound on the summation? Is it from negative infinity to infinity, or is it from 1 to infinity?
It's from, let me think about it. 0 to infinity. Okay, so I'll put that over here. R is equal to, I won't write the sum out yet. I put the sum there to remind you that in the end, we're going to have to sum everything up. And I'm going to have to sum up all possible, whoops, M. Yep. All possible M's, physical M's. and
A sub
all-
M, B sub M.
Is that the same M you used in that equation?
For the rest of this lecture,
Okay. But not for the beginning.
just in case.
But not for the part of this lecture that came before you wrote that.
Right.
Okay.
Okay. I was writing this over here. C sub L R to the L plus D sub L over R to the L plus 1. Okay? With understood that ultimately we're going to make sums out of all of these things with coefficients for the sums. So that's the radial part. Okay. Radial part done. Radial part done. Now I'm left with this thing here. All right? This thing here is hard to solve. And so it has a name. It's the Legendre equation. And Legendre solved the Legendre equation by assuming a polynomial solution and then finding the rules that apply to the coefficients on the solution. Solution has been found. Yeah, good. The general expression has been written. It's in the notes.
Yeah, we did this in quantum physics 1, so.
Okay.
And 2.
Yeah, and you'll do it again. So I'm going to skip the details here. And write. Yes. That the solutions look like this. I can transform that equation in theta, right, into an equation that looks like this, where I need, I am changing variables on you, and I set at some point here, 11, 13, I just want to make sure, yes. I made a simple substitution, which is that x is equal to cosine theta. And then that equation that I wrote there can be, it's not that hard to change it into this equation. Plus my empty, which I just,
Are those the operator symbols or just bigger parentheses?
bigger parentheses. Okay? So making that substitution, the equation looks like that. That's the form that we most frequently see of the Legendre equation. We're actually going to directly solve, yes?
What, is that a minus plus sign between the L's and the M?
The smudge.
Or is that just chalk?
Here?
It's a minus sign.
Yeah.
Okay, there we go.
That's just a minus sign. Okay, we're gonna address this problem in two circumstances. One is the one we'll discuss most extensively, and that's the case where m is equal to 0. And what that means, if I look over there, is that the azimuthal function is constant. So this problem has azimuthal symmetry. Right, or rather, I would assume, under situations where the azimuthal solution is constant, so it has something like cylindrical symmetry, but not. Right? That would be m equals 0. So we're going to start off by assuming that, and we can solve a specific couple of cases in using that assumption, which simplifies things. And then we'll go to the next stage where m is not equal to 0. Under that circumstance, then, the polynomial there, p sub l, right, has a generating function, a specific form that looks like this. The solutions to this equation both start with m equal to 0. This is the Lth derivative of x squared minus 1 to the L. Right? So the polynomial p sub L that solves this equation can be generated from this relation here. Okay? And we actually want to know the first few. So P0 of x is 1, P1 of x is x, P2 of x is, now it begins to get a little complicated, 3x squared minus 1 over 2. And P3 is 5x squared minus 3x over 2, generated from there. And remember that I made the substitution that x was cosine beta, so this would be cos theta. I won't bother to write it. Okay? There is, because of the fact that that's second order, a whole other set of solutions, right? Turns out that the other solutions end up giving us infinities at theta equals pi and 0. So those solutions we don't consider. Mathematically, they're fine, but this is the set of solutions. This is the set of Legendre polynomials that apply to the physical situation. Okay? So, for a situation where I have azimuthal symmetry then, so for m equals 0, write that here, Q is equal to a constant. R remains the same, and my solutions here look like that. They are P sub L's. So I can write, oops, that the voltage, the potential, as a function of R and theta, because phi has dropped out of the problem, is equal to the complete set and I guess I'm going to tell you right away that I always reduce the number of coefficients. I start my count of coefficients at A. So this A is not the same as that A. All right? A sub L, R to the L, plus B sub L, R to the minus L plus 1. So that's just what I had there, okay? Times P sub L cosine theta. So substitute cosine theta into X over there. Because this problem mathematically is a Sturm-Liouville equation, something that I referred to last time around, it turns out that the solutions do form a complete orthogonal set. And we can make them orthonormal by just putting in proper normalizations for each of the terms. Okay? So there it is. Okay, so what you didn't do in quantum physics, okay, is now apply boundary conditions to figure out what the solutions have got to be under certain boundaries. What you did was you just solved the general form of the equation and found out what the eigenvalues were, right? But here, now my solution is going to be some of those things, and I need to tell you what the boundary conditions are, and then figure out what the coefficients have got to be in order to satisfy those boundary conditions. All right. So there's, get rid of this. The generating functions and the definitions for the P sub L's can be found in Schaus, possibly in the back of this textbook, Ohanian, I'm not sure, but probably in a differential equations text as well. Let me tell you, I did tell you the most important or very useful aspect of these solutions here, which is that the integral from, I'll do it in theta. Zero to pi, P sub L of cosine theta, P sub L prime of cosine theta. Sine theta, d theta. That integral is 0 for L not equal to L prime, and it's 2 over 2 L plus 1 for L equal to L prime. Okay? So if I know what the potential's got to be, on a particular surface, for example, then I can plug in the appropriate, I know what the potential has to be on a particular surface. It's then got to be, I have my left-hand side, and then the sum on the right-hand side has got to add up properly, right? So let's say that now I define potential at radius r as a function of theta. Okay? Reason that I ended up choosing, I'm going to define it that way, is because this is a problem that's going to have spherical symmetry. So I'm going to define the potential on a spherical surface. Okay? Yeah. So I can rewrite that as I need to multiply it by a weighted function, and I need to multiply by the sine theta and by the p sub l. So I multiply both sides by p sub l of cos theta sine theta. Integrate. Over theta. All right. And now from this, I can figure out what the a sub l coefficients have got to be. Oh, this is the potential at position r, and so this becomes capital R in here. That's minus r to the minus l plus 1. Right? My solutions have got to look like this, given this potential on the surface. But I have the added constraint that I can apply, that if I'm going to solve for the potential outside of the radius r, right, then this term is going to go to 0. So I'll just put goes to 0 if r is greater than capital R. And otherwise, inside, outside, and inside, these terms are going to go to 0. Actually, I have to take that back what I just said. This has got to drop to 0 outside if the region over which I want to find my solution goes to r equals infinity. So these solutions have got to drop out for r goes to infinity. And these solutions have got to drop out for r goes to 0. If I have a problem in which r doesn't, I'm going to solve in a space where r does not go to infinity or to 0, then I need to include all of the solutions. So, for example, this problem, where I define the potential on a surface, and now I want to find the potential out here, I can drop out these solutions. This problem, where I have the potential on a surface, and I want to solve inside all the way to 0, I drop out those solutions. But this problem, two concentric, those are supposed to be concentric, spherical surfaces, where I want to solve in this region here, I have to keep all of the possible solutions. Okay? All right. So, I'm going to have a spherical example where the potential is specified on a surface. Let's see. I think that I'm going to choose a really simple potential. Similar than the one that's in my notes. Let's say I have a problem where the potential on a given surface, on this surface, is given by cosine theta. Okay? I would recognize that this problem here, right, this situation here, corresponds to P1. Right? It is a Legendre polynomial. It is one of these solutions, okay? That solution is orthogonal to all of the others. So that means when I go over there and I'm searching for a solution over there, the only ones that are going to survive, right, the integration, okay, are going to be the ones that are, that is, I have V here, V of R theta, is going to be L equals 1, right? So, because I specified my surface potential to look like that, I can go over here, let's see, and eliminate all of those. My integral is done. Over on this side, L is equal to 1. Over on this side, I've got, what I say it was 2 over 2L plus 1, which is 3, 5. L is 1, 3. And over on this side, I have just done my integration, and this is equal to 2/3 V0. Okay? I assert that that's true. So, now I've got to figure out, what I'm going to use here. I've only got these powers. The region that, if the region that I want to solve in is out here, is on the outside, then this term goes away, and my potential, I have to come back over there, but I'll just write that V0 is equal to V1 R to the minus 2. So I know what V1 is. It's the only term that survives. I come over there and I plug V1 in there, and that's what my solution looks like. Right? So outside, V of R theta is equal to, R squared V0 did that R to the minus 2 cos theta. That's what it looks like outside. Potential drops off as 1 over R squared. That's faster than we would have if I had a point charge, but there is no net charge there because the potential is equally positive and negative. So the potential is going to drop off faster than 1 over R, and it does. Okay? On the inside, if I wanted to solve, and I could, I've specified it on this surface here. On the inside, my solution would look like V of R theta in is equal to A1, oh now I've got to come back over here, and A1R is equal to V0, right? So A1 is equal to V0 over R. Yes? V0 over R, little r to the 1 cos theta. Okay? So I've got my potential inside and outside, but when I did that, when I solved inside, I only take these solutions. When I solve outside, I only take those solutions. And the two potentials actually make sense. Because I've got this cosine function, it turns out then that the average potential right at the center is going to be 0. You did that already, mean value theorem, right? And in fact, it does go to 0 at the center. I will just claim that that means that we did it right. Okay? But the magnitude of the potential grows linearly out to the edges to this point here, and then drops off as 1 over r squared as we go outside of this region. Okay. So that's a problem where I specify the potential on a spherical surface. And next time I will, because we are going to need to, go into spherical harmonics. Because we're going to use spherical harmonics as approximations. No, not as approximation. We're going to use what's called a multipole expansion for the approximation of the potential outside of any distribution of charge. If you have a finite distribution of charge, then it will turn out, if you go far enough away, the potential will be dominated by 1 power. We'll work that out for complex distributions. Okay. Someone's going to have to carry the aside box away and bring it back again, because I didn't have appropriate